So I'm going to talk about some models, some random models that we hope will mimic the behavior of prime numbers, and some pros and cons of these models. But to set up, I'm going to begin with a different sort of problem, and the connection will be made a little bit later in the talk. So the first problem I want to talk about is called the interval sieve problem. You take an interval, let's say from x to x plus y, so y represents the length of the interval, and we remove from that interval all the integers divisible by a prime below z. Okay, so it's a very basic sieve problem. A very canonical example is if we take the interval 0 to y and we sieve out all the numbers with a prime factor less than square root y. What do we have left? We have left the primes. And by the prime number theorem, we know, in fact, we have an exact formula for this. It's exactly the primes between square root y and y plus the number 1. And by the prime number theorem, it's asymptotic to y over log y. Okay, so that's one. Also, if we generalize this, so we change our cutoff for the prime sieving to y to the power 1 over u, then using the prime number theorem and some iterative techniques, one can show that, and also an asymptotic for this, in terms of something called the Buchstabe function. Now, the Buchstabe function is a function that does not have a simple elementary formula, but it has this delay equation. Okay, this is actually a special case of some of the equations that Andrew was talking about earlier this morning. And it's 1 over u between 1 and 2 by the prime number theorem, and then it has this delay equation formula. As u goes to infinity, it approaches e to the minus gamma very quickly. And this can be proved, for example, using the so-called fundamental lemma from the sieve. So here is a plot of the Buchstabe function. So it drops from 1 to 2 very quickly, and then it rises again, and then it very rapidly is approaching e to the minus gamma. Now, in fact, there are some oscillations up and down, and those oscillations will become very important in what I'll talk about later. Now, there's an equivalent formulation of this problem. So now I'm going to talk about what I call a residue sieve. So let A sub p will denote a residue class mod p for each prime. And capital A will be the aggregate of these choices for the primes up to z. And now I'm going to define this quantity s, y, z, a. So I'm going to take the interval is now 0 to y. And I'm removing not the integers divisible by p, but those congruent to a sub p mod p for each prime up to z. And by a very simple, essentially Chinese remainder theorem argument, the original problem I had on the previous slide is equivalent to a residue sieve where the residues are minus x mod p for each prime. So you could think of this interval sieve problem in two different ways, taking an arbitrary interval of a given length and removing all the integers that are divisible by a prime up to z, or starting with a fixed interval 0y and varying the residue classes. And what we care about are the extreme behaviors. So we fix y and z, and now we take the minimum or the maximum over x over our starting point. Equivalently, we fix y and z, and we take the minimum or the maximum over all possible choices of the residue class. And it turns out that both of these points of view are very important in the theory. In particular, you could think probabilistically in the residue sieve, if we fix y and z and we take these numbers a sub p completely at random, well, as we vary all the a sub p's, we're capturing all the integers. So it's a very simple, exact formula for the expectation of s, y, z, a over these random choices. And because of that, of course, the minimum must be less than or equal to the average and less than or equal to the maximum. This product here is very familiar to number theorists. There's an asymptotic formula due to Mertens. And I've put that at the top, so I've now incorporated the Mertens estimate into that middle expression. So that product over primes is asymptotic to e to the minus gamma over log z. And so again, ignoring some error terms, we get that. And now I'm going to define some quantities where I take, let's say, this minimum quantity here and divide by essentially this piece in the middle. Now I've switched from, I'm fixing now y to be z to the power v. So I'm fixing the ratio of the logarithms of y and z. So this is now normalized. So this ratio here will be at most 1. This ratio will be at least 1, at least asymptotically. And now I take the lim sup of that and the lim inf over here. All right, now there's a lot of little bits to unwind here to figure out what this means. And what it means is that if z is large enough, this s minus is always at least f0 of v times this expected value here from the random choice. And the s plus is at most capital F of 0 times the expected value from the random choice. And moreover, little f0 is the largest number with that property. Capital F0 is the smallest number with that property. Okay. So if you plug these definitions into this estimate at the top, you'll see that little f0 is always less than or equal to 1. Capital F0 is always greater than or equal to 1. Okay, so these have been normalized in a special way so that this will be true. Now, you might wonder, okay, are these two equal to 1? Can one do better? And yes, you can do better. And here's an example, again, coming from the prime number theorem. If we sieve the interval 0, z squared by the primes up to z, as I mentioned before, we're left with primes, so the prime number theorem gives this asymptotic. Equivalently, using a random, or using a residue sieve, you could take all your APs to be 0. And if you compute, what you get is an upper bound for little f0 of 2, which is strictly smaller than 1. It's about 0.890. So it's 1/2 e to the gamma.
Could it be that f0 is a lim inf and capital F0 is a lim sup?
No. This is like a minimax. Each of these are like minimax. So I want this to hold for every epsilon and z large enough. I want this to hold all the time. It's lim sup of s minus lim inf of s plus. Yes, I've actually had some discussion about that with some people, and yeah, it is that is the correct definition, because I want this to hold all the time. So it's the lim f0 represents the lim sup. If this quantity here occasionally gets super small, I don't care. I want to know how large it is.
And the inequalities you wrote there. I mean, the lim sup is bigger than s minus. I mean, asymptotically.
Maybe you should repeat the definition of s minus and s plus.
Okay. Yeah, S minus is the minimum over all x's. And I want the lim sup of this. I want to know how large this minimum is, how large it can be, infinitely often. Yeah.
I think the confusion is that using the letter X for this in class 24 when we started, it was the technique of your interval from X to X plus Y.
Oh, no, the length of the interval is always y. X is, I'm taking the minimum over starting points. Yeah.
Okay, but I mean, it's not just
Okay.
My objection is not the definition, it's just inequality you wrote after you define little and zero capital.
So S minus and S plus are different functions.
Because of this inequality here, if I divide by the thing in the middle, S minus is always less than or equal to 1. What, are you talking about the definition of...
That's my objection to it. Doesn't follow from the definition. But
Oh, okay. Yes, there might be something wrong with that. Okay.
the red inequality is fine. Sorry. I think this was my
Oh, okay. Okay. All right. Yeah, I apologize for that. All right. So just ignore the blue if you don't believe it. There's going to be a number of things that are going to be semi-arm waving in this talk.
The stick will help.
So, okay, the next person who asks a stupid question, how long does this reach? Yeah, gets this. All right, so here I'm repeating them. I want to talk about different estimates that are known for these. So if you apply something called the linear sieve, that gives you a lower bound for little f0 and an upper bound for capital F0. In fact, these are bounds for S plus and S minus that hold all the time. And these are called the linear sieve functions. They, again, are not elementary. They are defined iteratively using a delay equation. But they both approach 1 monotonically very quickly. Little f being increasing, capital F being decreasing, and these are from 0 to 2, they're simple formulas, but then after that, they have these delay equations. There's a little less obvious relation, which is the monotonicity of little f0 and capital F0. So little f0 is actually increasing, capital F0 is decreasing. And the basic reason is you can take a long interval and break it into the disjoint union of a bunch of short intervals. Okay, I'm not claiming it's strictly increasing. Yes, I do not like the terms non-decreasing and non-increasing because my students are always confused about those. They confuse non-increasing with not increasing. So I use increasing and strictly, and I'm not claiming anything about strict here. The other is what I mentioned before. If you apply the Buchstabe function, so you take x equals 0, that gives you another set of inequalities for little f0 and capital F0. Now, depending on whether this quantity inside is less than 1 or greater than 1, one of these is already is trivial, but the other might be non-trivial. So if you combine those together, all those inequalities, we have now inequalities upper and lower for little f0 and for capital F0. And for reference, I've included graphs of the sieve functions, capital F and little f. So notice also something about little f, it's 0 below 2. So when v is 2 or less, the lower bound here is not telling us anything. It's the absolutely trivial bound. And as v, or as s, well, okay, in this case I wrote s, so as the parameter approaches infinity, they approach 1 very, very rapidly. Now, this is an extremely important result that was discovered by Meyer in 1985. And if you look at the Buchstabe function minus its limit, it doesn't approach it monotonically. It has infinitely many oscillations, infinitely many sign changes. And as a consequence, if you plug that fact into these formulas here, you'll see that little f0 is always strictly less than 1. Capital F is strictly greater than 1. Okay, so that's very important. On the other hand, by quantifying these sign changes, the oscillations, Hildebrandt and Meyer showed that 1 minus f0 and f0v minus 1 approach 1 at approximately the same rate as the linear sieve functions do. Okay. But what happens when the parameters are small? In particular, what happens when v is equal to 2? This is going to be a very important special case that will come up in certain applications I'll talk about very shortly. So if we plug in v equals 2 into those inequalities from before, so f02 is somewhere between 0 and 1/2 e to the gamma. Capital F02 has a lower bound which is equal to this, which can be computed. The maximum is actually somewhere between 2 and 3. And an upper bound, which is e to the gamma. Okay, so at these small values, the upper and lower bounds, there's quite a bit of a gap between those. In some papers, I've seen a folklore conjecture. I'll call it a folklore conjecture. Some people have mentioned it, that they believe that it's true, that little f2 is 1/2 e to the gamma. Now let's translate that. What does that mean? It's another way of saying this is that for any starting value of x, if we sieve an interval of length y by the primes up to square root y, we can never have a residual set that is smaller than what we get from when we start at x equals 0. In other words, what we get from counting primes. Now you might wonder, okay, why? It's a conjecture. Why can't we prove it? I'm going to explain why we can't prove this. But there's some possible evidence that this is not the case. And that is in some work I've been doing with my postdoc, Mikhail Gabdulin, we've improved the lower bound for f0, capital F0 of 2. So what this means is that we can find examples of, well, we actually use residue classes. We use the residue version to show that, in fact, we can have a lot more elements remaining from the sieve. And we've been trying without success to use the same ideas to improve the value of F02, but this is very new work. So again, I mentioned that F02 is important. The importance will come out very shortly. But, okay, so here I've just repeated some of the inequalities I had before. And now I want to ask the question, can the lower bound here be improved, especially for v equals 2? For v equals 2, the lower bound is 0. Can we improve that to anything? Can we improve the upper bound here, coming from the linear sieve? Now, the linear sieve is known to be optimal, but it's known to be optimal because of certain examples of Selberg type. These are examples that come from parity-sensitive sets, like the set of integers with an even number of prime factors, a set of integers with an odd number of prime factors. Intervals are not parity-sensitive. So the question remains, so what this question is really about is the linear sieve optimal for intervals? Well, very interesting result that Granville proved just a few years ago, connecting the problem with the so-called Landau-Siegel zero problem, or the exceptional zero problem. So if there are exceptional zeros in the usual sense here, that you have a sequence of Dirichlet characters, quadratic characters, and associated zeros of their L function, which are sufficiently close to 1, then he proved that, in fact, these functions, little f0 and capital F0, are equal to the corresponding linear sieve problems, linear sieve functions. Okay, which would completely solve the problem of what's going on with the linear sieve. But such zeros, well, I think the common belief is that they don't exist. But it's been a notoriously difficult problem to prove that they don't exist. On the other hand, what this is really saying is that to answer any of these two questions here, to make any improvement on the lower bound here or the upper bound here, one has to first prove that the exceptional zeros don't exist. So it's giving some indication of how difficult this problem is. So already we can see that there's a connection between this problem and a very notorious problem about zeros of L functions. So in particular, if these exceptional zeros exist, little f0 of 2 really is 0. And correspondingly, capital F0 is e to the gamma. All right. Now I want to talk about something closely related. And now I'm going to start talking about random ideas to model the integers, to model the primes. So if, and this is about the sieve. What is a sieve? A sieve is when you take a bunch of integers and then you remove those divisible by small primes. That's what's called a general sieve. Now, and we care about estimating how many integers remain when we finish with this process. So there's a crude heuristic. And the crude heuristic is that if you take a random number and you take let's say a small prime p, the probability that that number is divisible by p should be about 1 over p. And if these primes are not too big, these events should be independent. So what that leads to is as a heuristic reasoning. If we count how many integers there are up to x that have no prime factors below t, by independence, this should be approximately x times the product of the primes up to t, 1 minus 1 over p. The Mertens formula gives an asymptotic for this, so we get e to the minus gamma over log t, times x. Now it is known, and possibly Demetrius will talk about that in his talk. Yes or no?
Larger t, yes, right, indeed, exactly.
Yeah, so for small t, x to the little o1, which is known as the Kubelius model, this is known to be very accurate. So this is correct. But what happens with larger t? Well, if we want to count primes, what value of t should we take? Well, square root x. So we plug in square root x, and let's see what our naive heuristic prediction gives. You plug in t equals square root x, and we get a prediction now for the number of primes up to x, which is of the right order, but with the wrong constant. Okay, 2e to the minus gamma is not equal to 1. It's a little bit larger than 1. So that indicates that there's something going on here, and what's going on is that when the primes that are large do not behave independently. Okay, but the next idea is due to Polya, and it seems completely crazy at first. Polya's idea, from a little expository paper he wrote in 1959, take t to be x to the power 1 over e to the gamma. Okay, now why did he chose that? Because, well, if we sieve the integers up to x by the primes up to x to the 1 over e to the gamma, we're still left with essentially all the primes, with very few exceptions. So the left side is very close to pi of x, the number of primes up to x. But now this naive heuristic gives the right answer. So what we've done is we've taken a heuristic which is clearly wrong, and we just, waving our arms, we fudge it to make it give the right answer. And there was some, controversy about this. Okay, you fudge your model to give the right answer. Is there any validity in doing that? Okay, I think the last talk was largely on that topic. But at this time in the 1950s, maybe the idea was not so well spread. And Polya has this very interesting quote that he wrote in the paper, saying that he doesn't really understand why this cutoff should work, except that it does. And actually justifying it by saying, well, certain ideas from physics were shown to work, but nobody understood really why at the time. The criterion of a physical theory is its applicability. Okay, so if something works, use it, basically, is Polya's motto here. So we're going to actually see very, very soon that this idea can be used to model other things, not just counting the number of primes up to x. And it can be very useful in that context. We can do things with it that we can't do with other methods. All right. So now I want to talk about a very famous model of primes, which was the very first one ever created by Cramer in 1936. And he started with the prime number theorem, which says that the density of primes near x is about 1 over log x. So he created this random set where each integer, from starting at 3, you flip a coin that comes up heads 1 over log n of the time. And the ones that are heads, you add to your set. So, and you do this independently. So you choose numbers independently to be in your set with probability 1 over log n. And because of independence, you can very easily prove certain facts about this. Now, Cramer was interested in modeling, using this to model the largest gap between the primes up to x, which still is very mysterious today in terms of what we can prove. So one of the things he proved, and I'm going to mention quite a few consequences of this model, is that if you count the number of elements up to x that are in this, it's Li of x plus an error, which is x to the 1/2 times some logarithmic term. And all these facts I'm going to be mentioning happen with probability 1. Okay, so with probability 1, this happens. And, well, we know, or we hope, that the primes have this same property. It's equivalent to the Riemann hypothesis, so that's looking good. So in terms of large gaps, Cramer showed that the lim sup of this difference is equal to 1. And he used that to make the same prediction about the primes. So the Cramer set also satisfies some information about k correlations. So you take a non-empty finite set H, and you want to know how often are all the numbers n plus h in your set, where h lies in script h. So it's asymptotic to x over log x times the size of h. That's for any h. In terms of intervals that are longer than what he showed for the largest gap, as long as h of x grows a little bit faster than log squared of x, if you count the number of elements between x and x plus h of x, that's asymptotic to h of x over log x, which is the expected value, but you actually always have that number. This last one is a little bit more complicated to state, but basically we're counting gaps between elements which are at least lambda times the average gap. So log x is the average gap for the elements up to x. How many, and again, because of independence, that you can write down very quickly a formula, an approximate formula, and then when lambda is not super large, this is approximately e to the minus lambda times x over log x. So one has an exponential distribution for gaps between elements here. And also one has independence over there's because of the independence here, this is another way of saying this is that this sequence here behaves like a Poisson process with intensity 1. All right, so let's examine carefully some of these properties, and now I want to compare with what we expect or what we can prove about primes. So in terms of global distribution, if you count the number of elements in the Cramer set minus the logarithmic integral divided by square root x over the square root of x over log x, this, by the central limit theorem, is a Gaussian with mean 0, variance 1. In particular, the numerator has variance x over log x. Now, interestingly enough, Cramer himself, in an earlier paper, showed that if the Riemann hypothesis is true, the variance for actual prime counts is smaller. It's x over log squared of x. Again, now I have to average over, let's say, a dyadic interval. So what's going on? Why is there a discrepancy here? Well, the discrepancy essentially is because the Cramer model does not know anything about the Riemann zeta function. And in particular, it doesn't know that there's this a complex function out there whose zeros are governing what's going on with the primes. So there's this model that originally due to Vintner, expanded by Montgomery and Rubinstein and Sarnak, that if you assume the Riemann hypothesis and that the linear independence of the positive imaginary parts of the zeros of zeta, then one can prove that this ratio, now pay very close attention to the logarithm here, is not under the square root, whereas it is up here. That ratio has a limiting distribution, and that limiting distribution is not Gaussian. In fact, it's symmetric about -1, and it has much lighter tails than Gaussian. In fact, the tails decay doubly exponentially. Okay, so again, that is a flaw in the Cramer model. What about what happens in what I call long intervals? By long, I mean larger than log squared x. So this is a restatement of what I had on a previous slide. Well, the good news is that in 1943, Selberg showed that if the Riemann, I should have written here. Okay, this is under the assumption of the Riemann hypothesis. For the same h, then almost all integers have the same property for actual primes. So that's the good news, that it matches the Cramer model. However, Meyer came along in 1985, invented something called the matrix method, which shows that there are intervals with an arbitrary power of log, the length being an arbitrary power of log, which do not satisfy this. In fact, the lim inf is less than 1, the lim sup is greater than 1. And if you go through Meyer's method, what he is actually showing is that the left side here, the lim inf is at most little f0, and the lim sup is at least capital F0. So understanding the values of little f0 and capital F0 have direct implication for the oscillations of primes in these intervals. Okay, so that's another flaw in the Cramer model.
How n is connected with x?
This is x. It's x in a very special font.
Change my glasses.
Yeah, it's an x. Yeah. Okay. Okay. Now, what about large prime gaps? This was Cramer's initial motivation for studying this model. What we know about g of x, the largest gap between primes up to x, is very poor. I mean, the upper and lower bounds are vastly different. Even if we assume the Riemann hypothesis, the best we can do as an upper bound is around x to the 1/2. And, but Cramer conjectured that actual prime gaps should behave like his model. There are a couple of newer conjectures that where the order of magnitude is the same, but the constant is different. Granville, I'm going to talk about his model soon, showed that, or conjectured that the constant should be at least this 2e to the minus gamma. In work with Bill Banks and Terry Tao, we think that we now have a conjecture that it's asymptotic to the log squared x over little f of 0 of 2. So the value of that is rather important. The computational data is rather unconvincing. It doesn't match any of these. The black being the actual largest prime gap, and this is a strange, what I call a log squared x scale on the x-axis here. Green is Cramer. The red is the lower bound from Granville's model, and that also follows from the model I have with Banks and Tao. So I think it's just because log of x is very small in this range, and we'd have to go up way, way, way far out in order to really see what's going on.
So if f0 of 2 is 0, you think it should be, the conjecture says it should
Yeah. So
be proving the Riemann hypothesis.
if these exceptional zeros exist, this right here, well, it's no longer an asymptotic, but what we conjecture is that the order of this is strictly larger than log squared x. It's actually a larger order.
So I'd just like to say I really have greater than your conjecture as my conjecture. And then knowing that F02 is related to.
Oh, okay, yeah. I mean, as you're going to see, the F02 really is built into your model. Yeah, it is built in. So I want to talk about the K correlations, and this is another big flaw in the Cramer model. So here's again the what's called the Hardy-Littlewood conjecture for k-tuples of primes. So you have a set H, finite set. You want to understand when is n plus h prime simultaneously for all the little h's in your capital H. And you get this ratio here, but then there's this fudge factor, this extra factor, which is written as an Euler product. And comparatively, the Cramer model doesn't have it doesn't have this factor. It's simply missing. And that factor comes from the distribution, what we know about the distribution of primes in modulo small primes. Like the primes, very few of them are 0 mod 2, very few of them are 0 mod 3, 0 mod 5, and so on. So the Cramer model doesn't see the fact that actual primes avoid 0 mod 2, 0 mod 3, and so on. Here's a couple examples. So if H is the set 0, 2, that's for counting twin primes. So the twin prime constant, which is this, is about 1.32. That's not 1. And if H is 0, 1, of course, then because if you look at the prime 2, there are 2 residue classes mod 2. So this first factor is 0. So this constant is 0. But the Cramer model has lots and lots of pairs of consecutive elements with high probability. So that's the most, I would say, well-documented flaw in the Cramer model. Granville's refined model was designed to correct this flaw. So we fix a number x, large number x, and take some parameter t, which grows a little bit slower than log x. And now I have this set ut, which is the set of integers that have no prime factor below t. If n isn't in that, which means that there is a prime factor below t, we just don't take those integers at all. And then we independently choose the integers that are in ut with this probability. And that numerator is designed to correct the global density to make sure that the number of integers in this set up to x is still about x over log x by the prime number theorem. And so it not only satisfies the prime number theorem, but it also satisfies the analog of the Hardy-Littlewood conjectures, okay, which is what it was designed to do, okay. And so in 1995, Granville showed that this now ratio is at least 2e to the minus gamma. But essentially, what's in the paper was 1 over little f0 of 2, assuming that the right-hand side is finite. So just by reinterpreting a few things in the paper, we've showed this. So again, little f0, 2, knowing that value would help us with some of these conjectured results for large prime gaps. Okay, now I want to talk about a new model, this model I have with Bill Banks and Terry Tao. So again, I'm not going to worry about error terms. This is just the standard Hardy-Littlewood conjecture. And I want to decompose this Euler product into 2 pieces and analyze each piece separately. Now, the product here is a product over all primes, but it converges very rapidly. So if I take a large number z and I truncate it at the primes up to z, it's a very good approximation. Well, now I have a finite product over here. This I can handle with Mertens. And now what is this now? This is, up here I have the number of residue classes occupied by H modulo P. This has a probabilistic interpretation as the probability that H lies in a certain random set SZ. Now what is this random set? It's the set of integers that are not in any of the residue classes AP mod P for P up to Z. Something I talked about way back at the beginning of the talk. But now the APs are chosen randomly. So this is a very easy calculation to show this. And now we reintroduce Polya's crazy magic idea, which is to choose z to be around x to the 1 over e to the gamma. Then this factor here, e to the gamma log z, is very close to log x. And this factor here neatly cancels out the denominator here. And what we're left with is a version of the Hardy-Littlewood conjecture for counting k-tuples of primes that says this is asymptotic to, now I've divided by x, so that's the proportion of integers with that property, is the probability that h lies in s z of x, where z of x is now given here. And the advantage of this is that there's no complicated Euler product anymore. That has disappeared. And using this as a base, we created another random model of primes, and this random model of primes was simply given by this formula where, okay, I've given a much more precise definition of z of x, which you can ignore at this point. And we have then, with very high probability, not only an asymptotic for the Hardy-Littlewood conjecture, but a version that gives a main term, which is similar to that of the prime number theorem, with a power-saving error term uniformly over a big range of these sets H. Okay, now the exact details are not so important there, but the point is we have a very, very precise Hardy-Littlewood conjecture. And again, now this is a much more complicated calculation, but we have a theorem that says, tells us about the gaps in this set. And again, this 1 over little f02 is appearing. What makes this more complicated is that whether or not two numbers are in our set, they're no longer independent anymore. We don't have the independence. Because if a number is in the set, then n plus 1 is automatically not in the set because we're excluding some residue class mod 2. So we have the same, the same guess here, or the same property as the Granville model. Granville's model does not have quite this, doesn't have Hardy-Littlewood conjectures with this strong of an error term. So that's one of the advantages of our method. I was going to talk briefly about some of the ideas where this little f02 comes from. And it comes from looking at the very small primes. So the basic idea is if you have an interval of length x, the product of the primes up to epsilon log x is around x to the epsilon. So you get zillions and zillions of independent copies of those. And you take the, say, maximum gap in that set, and then you focus on those. Again, I'm running out of time, so I'm not going to say much about that. I did want to talk about, for just a few minutes, about this idea of counting how many prime gaps are at least a constant times the average. Now, Gallagher showed that if we assume a suitable uniform version of the Hardy-Littlewood conjectures, again, we get this exponential distribution coming out, which matches what we had from the Cramer model. But now, wait a minute. The Cramer model did not see the Hardy-Littlewood conjectures. The Cramer model did not match the Hardy-Littlewood conjectures. So why are we getting the same answer and the same? And the reason is because if you suitably average this quantity here, the average is 1. Okay, and in Cramer's model, it's equal to 1 all the time, but in reality, the average is 1. And this is some actual prime data. I'm getting ready to finish here soon. These are for a particular x, 4 times 10 to the 18th, and this is the value of lambda. And what here is, this is a logarithmic scale. This is the proportion of primes whose gap is at least lambda times log x. Now, what Gallagher predicted is that this should be e to the minus lambda. And on a logarithmic scale, that should be a straight line, which it really does look like it is a straight line. It looks really good. Except it's the wrong slope. This is e to the minus lambda. This is e to the minus some constant times lambda where the constant's bigger than 1. I believe that the discrepancy is due to the fact that even at this huge value of x, log x is very tiny, and there's some secondary terms which are rather significant for this small value of x. In fact, what I believe happens in the limit, if x were allowed to grow very, very quickly, this graph of the actual prime counts should match this and start actually bending upward above it. Okay, and that's why I want to explain in the next couple slides. So Gallagher's proof relied on an average of the singular series over certain k-tuples. This was extended by various people, but it's very hard to make this uniform in K. The uniformity in K is the key idea here. And if we reinterpret the Hardy-Littlewood conjecture in the form that I had with Banks and Tau, in fact, this reinterpretation is much easier to deal with, and we can succeed in averaging this over much, much larger k-tuples. So k being a power of log x instead of just double log of x. And this is something a graduate student of mine is working on. And so if you assume a suitable version of the Hardy-Littlewood conjecture with a power-saving error term uniformly in some range, again, you don't need to pay attention to that, then, and this is for any set that satisfies these, in particular, if the primes have this property, then the proportion of elements whose gap is at least, or is at least lambda times the average does have this e to the minus lambda uniformly, actually, in some rather large range. However, okay, that's good. That matches what we have with Gallagher. However, if lambda is rather large, like a power of log, then the proportion of elements whose gap is at least lambda times log x has this behavior. Now, f0 of this is a number which is less than 1, less than 1. So it's e to the minus, let's say, 0.99 lambda instead of e to the minus lambda. And that would correspond to a graph going out this way rather than where it appears to be with that limited data. Yeah. And we think that the cutoff from asymptotic to non-asymptotic is fairly close to this value here with exp of double log, triple log. Okay, but that's just a guess, and that's work in progress right now. So, all right, I think I'll stop here. Yeah. And apologies for the mistakes earlier.
Thank you. Thank you, Kevin. Any questions? Andrew.
A quote? Okay.
Well, you used this xe to the minus gamma model.
Yeah.
And in Harvey Littlewood's original paper in 1922, they commented on that model saying, probability is not a notion of pure mathematics, but philosophy of physics.
What
Yes,
years
yes,
ago?
yes. Well, to be fair, in 1922, probability had not been placed on a firm foundational basis at that time. That waited till the 1930s, but yeah. Anyway, yeah.
One other historical comment, I think that the oscillation, in some of Hendrik's early work.
The oscillation of the Buchstabe function.
Yeah, this sort of thing and related sieve functions. Anyway, Maya also did a beautiful job there. I wanted to ask you this result you have of Gabdulin. What does the construction look like? Sorry, it's way back.
Oh, whoops. That's the problem when you reveal your slides little by little. Oops. There.
Yeah.
Well, like I said, we're using the residue version. So we've had two approaches. One which is to look at different behavior of primes in certain residue classes. And another is to look at different behavior of primes in intervals, somewhat similar to these multiplicative functions that you were looking at earlier. So I think this idea, this bound here, comes from taking AP to be 0. Okay, so we're sieving between y, primes up to square root y. So the primes between y to the 1/5 and y to the 1/2, we take AP to be 0. And for the smaller primes, we take AP to be either random or use a greedy algorithm. It gives the same bound.
It's a bit like
Yeah. Kind of, but for reasons we don't fully understand, it's giving a much larger value for of the residual set. We've tried tweaking that to try to improve this upper bound here. I mean, there's no hope of improving the lower bound unless we want to first solve the exceptional 0 problem. But this upper bound, I'm not convinced that this is the true value. I think people have been guessing it simply because we have no other ideas of how to attack this. Yeah, we're again, this is something we've only recently started looking at. Yeah.
We have time for a question. Oh. Is there any chance of a random model for the primes that would duplicate the Mayer effect?
Oh, the Meyer effect. Okay. I didn't mention it, but both Granville's model and the model I have with Banks and Tao have the same extremal behavior on intervals of log to the c of x, as it captures the Meyer oscillations. They both capture the Meyer oscillations, yes. That's something actually we mentioned in our paper.
Maybe a quick one, James, yes?
These capture the limiting distribution of the difference between pi of x and lie of x?
I do not, I haven't, we haven't tried, especially our model, because we lack independence. We haven't tried to analyze that, but my guess is the answer is no. My guess is that the variance will be similar, at least order-wise, to that of the Cramer model, which is quite a bit larger, a larger order than that of primes under RH. Yeah. But again, that's not, we haven't actually analyzed it. That would be an interesting exercise, well, maybe perhaps more than an exercise to actually work out what the distribution is. Yeah.
Okay, so let's thank Kevin again.